What if everything you thought you knew about who belongs in computer science was completely backward? What if the greatest minds in computing history were systematically erased from textbooks, and the stereotype of who can code was manufactured rather than natural? Tonight we're going to explore a question that might make you uncomfortable. Are women better computer scientists than men? But more importantly, we're going to discover why this question itself reveals something profound about how we think about ability, intelligence, and who gets to shape our technological future. We're going to journey through time, uncover hidden histories, examine scientific evidence, and challenge assumptions that have shaped an entire industry. This isn't just a story about gender, it's a story about how we define excellence, how we create barriers, and how we can build a better future. Let's find out. Before we dive deep into this question, we need to understand what's at stake here. This isn't just an academic debate or a question of political correctness. The answer to this question affects billions of dollars in innovation, millions of career decisions, and the future of technology itself. When we exclude half the population from computer science, either through active discrimination or subtle discouragement, we lose perspectives, solutions, and innovations that could change the world. We risk creating technology that serves only half of humanity well. We risk perpetuating systems that embed bias into the algorithms that increasingly govern our lives. The stakes couldn't be higher. Understanding gender and ability in computer science isn't just about fairness. It's about whether we want the best possible technology, created by the most diverse and talented pool of minds available. Consider this. Every algorithmic decision that affects your life, from what you see on social media to whether you get approved for a loan, from how your medical diagnosis is made to which job applications reach human eyes. These algorithms are built by people. And if those people all think alike, if they all come from similar backgrounds and experiences, then the technology they create will have blind spots. It will fail for the people who weren't in the room when it was designed. Think about facial recognition systems that couldn't recognize black faces because they were trained primarily on white faces. Think about voice assistants that struggle to understand women's voices because they were tested primarily with male voices. Think about car safety features designed around male crash test dummies that left women more vulnerable to injury. Think about medical research that excluded women and then applied its findings universally. These aren't theoretical problems. These are real failures that have real consequences for real people. And they happen because the people building technology don't represent the full diversity of humanity. When we ask whether women are better computer scientists than men, we're really asking, can we afford to continue building our technological future with only half of humanity's talent? Can we afford to let stereotypes and bias determine who gets to code, who gets to innovate, who gets to shape the digital world we all inhabit? The answer clearly is no. But to understand how we got here and how we can move forward, we need to go back to the beginning. We need to understand the hidden history of women in computing, a history that's been largely erased from popular consciousness. To understand where we are today, we need to go back to the very beginning of computing. And here's the first shock. The first programmers were women. Not just some women, not just a few pioneers, but the field of programming was initially considered women's work. In 1945, when the United States Army built ENIAC, the electronic numerical integrator and computer, they needed people to program it. The hardware engineers were men, but the programmers, the people who actually made the machine do useful work, were 6 women. Betty Snyder Holberton, Jean Jennings Bartik, Kathleen McNulty Mauchly Antonelli, Marlin Westcoff Meltzer, Ruth Lichterman Teitelbaum, and Frances Billa Spence. These women weren't assistants or helpers. They were the programmers, working without programming languages, without operating systems, without any of the tools we take for granted today. They were given blueprints of the ENIAC and told to figure out how to make it work, and they did. These ENIAC programmers had to understand the hardware at the deepest level. They physically rewired the computer for each new program, connecting cables and setting switches. They crawled inside the massive machine, which filled an entire room, to debug it when things went wrong. They invented subroutines, the fundamental building blocks of all modern programming. They invented breakpoints for debugging, the technique we still use today to find errors in code. They created the fundamental concepts that all programming still uses today. And yet, for decades, their contributions were overlooked. When ENIAC was unveiled to the press in 1946, the 6 programmers weren't introduced. The focus was entirely on the hardware engineers. The women who made the machine actually useful were invisible. This wasn't an accident. It was the beginning of a pattern that would repeat throughout computing history. Women would do groundbreaking work, and then that work would be minimized, forgotten, or attributed to men. The ENIAC programmers prepared the machine for its public demonstration, writing the programs that would showcase its capabilities. But when the press arrived, they were asked to step aside. The photographs from that day show men standing proudly next to the machine. The women who programmed it are nowhere to be seen. Let's go back even further. Before the ENIAC programmers, there was Ada Lovelace. In 1843, more than a century before the first electronic computer, Ada Lovelace wrote what is considered the first computer program. She was working with Charles Babbage on his proposed analytical engine, a mechanical computer that was never built in his lifetime. But Lovelace saw something that Babbage himself didn't fully grasp. She understood that the machine could do more than just calculations. She envisioned that it could manipulate symbols according to rules, that it could create music or art, that it could be a general-purpose computing device. Her notes included an algorithm for calculating Bernoulli numbers, making her the world's first computer programmer a full century before computers existed. Lovelace wrote, "The analytical engine weaves algebraic patterns just as the jacquard loom weaves flowers and leaves." She understood the profound implications of what she was describing. This wasn't just a calculator. It was a machine that could process any kind of information, as long as that information could be represented symbolically. Ada Lovelace was the daughter of the poet Lord Byron, and she inherited both his creative imagination and her mother's mathematical talent. She had to fight against the expectations of her time, when women weren't supposed to study mathematics at all. She had to sign her groundbreaking notes with only her initials, hiding her gender to be taken seriously. And even then, for over a century, her contributions were minimized. Some claim that Babbage had really written her notes, that she was just transcribing his ideas. But historical research has proven definitively that the ideas were hers. The vision of the computer as a general-purpose information processor, the concept that would eventually give us everything from word processors to video games to artificial intelligence. That vision originated with Ada Lovelace. And she conceived of it when she was just 27 years old, working in an era when women were actively discouraged from intellectual pursuits. Fast forward to World War II. While the ENIAC programmers were inventing software engineering, another woman was creating the foundation of modern programming languages. Grace Hopper was a United States Navy Rear Admiral and a computer scientist. she created the first compiler, a program that translates human-readable code into machine language. Before Hopper's compiler, programmers had to write in machine code, the ones and zeros that computers understand directly. This was incredibly tedious and error-prone. Hopper believed that programming should be accessible to more people, that we should write instructions in something closer to human language. Her work led directly to COBOL, one of the first high-level programming languages, which is still in use today running critical systems in banking, insurance, and government. COBOL programs process an estimated 85% of all business transactions worldwide. Grace Hopper's vision of human-readable programming languages transformed computing from an esoteric specialty into something that could be practiced by many more people. Grace Hopper also popularized the term debugging after she found an actual moth causing problems in a computer, though the term had been used before in other contexts. But more importantly, she fought against the idea that we've always done it this way. She believed in innovation, in making computing accessible, in questioning assumptions. She once said, "The most dangerous phrase in the language is, 'We've always done it this way.'" These weren't just technical contributions, they were philosophical positions about what computing should be and who it should serve. Hopper understood that the future of computing depended on making it more accessible, not more obscure. She fought against colleagues who thought that programming should remain a specialized skill practiced by a small elite. She won awards, she rose to the rank of Rear Admiral, and she influenced generations of computer scientists. And yet, how many people today know her name compared to the names of male tech founders? So here's the rehook, the twist in our story. In the early days of computing, programming was seen as clerical work, like typing or filing. It was detail-oriented, required patience, and didn't seem as important as building the hardware. So it was assigned to women. The men were the engineers, designing the circuits and building the machines. The women were the programmers, making the machines actually do something useful. But here's the thing. As computers became more central to business and society, as programming became recognized as intellectually demanding and valuable, something changed. Men began to enter the field in larger numbers, and as they did, the perception of programming changed. Suddenly it wasn't clerical work anymore. It was engineering, it was mathematics, it was creative problem solving. It required brilliance and insight. And with that shift in perception came a shift in who was encouraged to pursue it. This transformation didn't happen by accident. It was driven by conscious decisions about how to professionalize the field. In the 1960s, as companies recognized that software was becoming a significant expense, they wanted to hire ideal programmers. Psychologists William Cannon and Dallas Perry were hired to develop an aptitude test for programmers. They surveyed 1,400 people to develop this test, and 1,200 of them were male, even though the industry at the time was more than 50% women. This biased sample created a test that favored men, and specifically introverted men. The test claimed to identify people with the right personality for programming, and those people turned out to be, surprise, mostly men who fit a particular stereotype, antisocial, mathematically inclined, more interested in things than people. This test was hugely influential. It literally trained the industry in hiring programmers, as one researcher put it, and it systematically excluded women. By the 1980s, computer science departments in universities saw a dramatic decline in the percentage of women students. In 1984, about 37% of computer science degrees went to women. That number has been declining ever since, hitting a low of around 18% in the early 2000s. Today it's only slightly better, hovering around 20 to 23% depending on the institution. What happened between 1984 and today? Did women suddenly lose the ability to code? Did something about programming change that made it unsuitable for female brains? Of course not. What changed was culture and perception. What changed was who got access to computers at a young age. What changed was how computers were marketed and who was shown using them. What changed was the stereotype of who belongs in computer science. When personal computers started appearing in homes in the 1980s, they were marketed almost exclusively to boys. Advertising showed boys and men using computers for games and learning. Girls were shown playing with dolls or doing traditionally feminine activities. Parents bought computers for their sons' bedrooms but not their daughters'. This wasn't a conspiracy. It was a series of marketing decisions based on assumptions about who would be interested in computers. But those decisions had profound consequences. By the time students arrived at college to study computer science, many of the male students had years of experience playing with computers. The female students, on average, had less exposure. This created a perception gap. The male students seemed naturally talented. They already knew how to code. The female students seemed like they were starting from behind. But this wasn't about natural ability. It was about opportunity and access. Teachers and counselors reinforced these patterns. They steered boys toward computer classes and girls toward other subjects. Sometimes this was explicit. Boys are better at computers. More often it was subtle, showing more enthusiasm when boys expressed interest, giving boys more attention and help in computer classes, calling on boys more often to answer questions. These small biases accumulated. Girls began to internalize the message that computers weren't for them. Even girls who were interested in computers started to doubt whether they belonged. The stereotype emerged. Computers are for boys, programming is for guys, the tech world is male. This stereotype became self-reinforcing. Fewer girls studied computer science, which meant fewer women in tech companies, which meant fewer role models for girls, which meant even fewer girls studying computer science. The cycle continued, generation after generation, until people forgot that it hadn't always been this way. People forgot that women had been the first programmers, but stereotypes aren't just about representation. They have real psychological effects that can actually impair performance. Research on stereotype threats shows that when people are reminded of negative stereotypes about their group, their performance actually suffers. This is one of the most robust findings in social psychology. Here's how it works. If you take a group of women and men with equal mathematical ability and you give them a difficult math test, their performance will be similar. But if, before the test, you remind the women that men are better at math, the women's performance drops. Not because the reminder changed their actual ability, but because it created anxiety and cognitive load. Part of their brain is now worried about confirming the stereotype, and that worry interferes with their ability to focus on the test. Meanwhile, the men's performance stays the same or even improves, because the reminder reinforces their confidence. This isn't because the stereotype is true, it's because the anxiety about the stereotype interferes with performance. Studies have shown this effect across many domains. Women taking computer science tests perform worse when reminded of gender stereotypes. Black students taking academic tests perform worse when reminded of racial stereotypes. Elderly people taking memory tests perform worse when reminded of stereotypes about aging. The stereotype itself creates the appearance of difference where none actually exists. And here's the crucial part. When you remove the stereotype threat, the performance gap disappears. In one study, researchers told students that a math test had never shown gender differences. Under those conditions, women and men performed equally. In another study, they told students the test was designed to be gender fair. Again, equal performance. The stereotype threat effect is so powerful that it can create artificial gaps of 10 or 15 percentage points on test scores. This means that much of what we observe as gender differences in performance might actually be the result of stereotype threat rather than real differences in ability. So let's address the question directly. Are there biological differences between male and female brains that would make one sex better at computer science? The research is clear. No, there are no cognitive differences between men and women that would predict success in computer science. Brain imaging studies show more variation within each sex than between the sexes. Yes, on average, men and women show some differences in brain structure and function, but these differences don't translate into differences in ability to code, to think logically, to solve problems, or to understand abstract concepts. Individual variation swamps group differences. You can't predict someone's programming ability from their gender any more than you can predict it from their height or hair color. The differences within each gender are far larger than any average difference between genders. There are brilliant male programmers and mediocre male programmers. There are brilliant female programmers and mediocre female programmers. Gender doesn't determine which category you fall into. Some people point to differences in spatial reasoning or mathematical ability, suggesting these might advantage men in technical fields. Let's examine this claim carefully. It's true that, on average, men perform better on certain types of spatial reasoning tests, particularly three-dimensional mental rotation tasks. On these specific tests, men score about half a standard deviation higher than women. But here's what that actually means. The distributions overlap by about 80%. Most men and most women have similar spatial reasoning abilities. The difference is in the tails of the distribution. There are more men at the very high end and the very low end. But even this difference is not as simple as it seems. First, these differences fluctuate based on how the test is framed. When the same spatial reasoning task is described as an art task rather than a math task, the gender difference disappears or even reverses. When spatial reasoning tests are framed as tests of creativity, women perform better. This suggests that the differences aren't hardwired, but are influenced by expectations and framing. Second, these differences vary dramatically across cultures. In some countries, there is no gender gap in spatial reasoning at all. In others, the gap favors men. In still others, it favors women. If spatial reasoning ability were determined purely by biology, we would expect to see consistent differences across all cultures. The fact that we don't suggests that cultural factors play a major role. Third, spatial reasoning can be improved with training. Studies have shown that just a few hours of practice with video games that involve spatial reasoning can eliminate gender differences in performance. If the differences were innate and immutable, they wouldn't be so easily changed by experience. Fourth, and most importantly, the relationship between spatial reasoning and programming ability is not as strong as people assume. Yes, visualizing data structures or understanding algorithms can involve spatial reasoning, but programming also requires many other skills: logical thinking, attention to detail, creativity, communication, persistence. there's no reason to think spatial reasoning is the most important skill for programming success. Now let's talk about mathematical ability, another domain where people often assume men have an advantage. The research on gender differences in math ability is extensive, and the findings are clear. Gender differences in overall math performance are trivial. Large-scale studies involving millions of students show that the average math performance of boys and girls is essentially identical. The difference is so small, less than 1/10 of a standard deviation, that the distributions are 95% overlapping. This means that knowing someone's gender tells you almost nothing about their math ability. But what about high performers? Some people argue that while average ability is equal, there are more men at the very high end of mathematical ability. The data on this is mixed, but let's assume for the sake of argument that it's true. Even if men outnumber women 2-to-1 among math high performers, this small difference can't explain the 5-to-1 ratio of men to women in senior computer science positions, or the 7-to-1 ratio in prestigious awards, or the pay gaps that persist even after controlling for experience and education. Moreover, whatever gender differences exist in math, high performers have been rapidly closing over time. In the 1980s, there were more than 13 high-performing boys for every high-performing girl on standardized math tests. By the 1990s, that ratio had dropped to less than 4-to-1. Today, it's about 2-to-1. If these differences were due to innate biological factors, they wouldn't be changing so rapidly. The fact that the gap is closing suggests that it's primarily due to cultural and educational factors, not biology. And here's another crucial point. The gender gap in math performance varies dramatically across different US states and different countries. In some states, there is no gender gap at all. In countries with greater gender equality in social policy, the gender gap in math performance disappears or even reverses. If math ability were determined by biology, we wouldn't expect to see these cultural and geographic variations. The evidence overwhelmingly points to cultural and environmental factors, not innate biological differences, as the primary cause of whatever gender differences we observe in math performance. But focusing only on math and spatial reasoning ignores other cognitive abilities that are just as important for computer science. Language ability, for example, is crucial for programming. You need to be able to read and understand documentation, communicate with team members, write clear comments and documentation for your code, present your work to others. On tests of language ability, women consistently outperform men by about 1/4 to half a standard deviation. This advantage has remained stable over time, unlike the declining advantage men have in math. If we were really trying to predict programming ability based on cognitive skills, we should be predicting that women would be better programmers because of their language advantages. But of course, that would be just as wrong as predicting that men would be better programmers because of spatial reasoning. The reality is that programming requires a diverse set of skills, and different people bring different strengths. Some programmers are exceptionally good at visualizing complex systems. Others are exceptionally good at communicating and collaborating. Some are detail-oriented perfectionists. Others are big-picture thinkers. There's no one profile of a successful programmer. In fact, when we look at actual performance in computer science courses and careers, women often outperform men when given equal opportunities. Multiple studies of undergraduate computer science programs show that women earn equal or higher grades than their male peers. Women are just as likely to complete difficult programming assignments successfully. They're equally capable of understanding complex algorithms and data structures. In some studies, women actually have higher grade point averages in computer science than men. The difference isn't in ability, it's in retention. Women leave computer science programs and tech careers at higher rates than men, not because they can't do the work, but because of the culture and environment. Women in computer science programs report feeling less sense of belonging than their male peers. They report less confidence in their abilities, even when their actual performance is equal or better. They're more likely to experience what's called imposter syndrome, the feeling that they don't really belong and that their success is due to luck rather than ability. And these feelings aren't irrational. They're responses to real experiences of being undervalued, overlooked, or discriminated against. Let's talk about some modern pioneers who prove that excellence in computer science has nothing to do with gender. Radia Perlman invented the spanning tree protocol, a fundamental technology that makes modern computer networks possible. Without her work, the internet as we know it couldn't function. The spanning tree protocol solves a crucial problem in network design: how to create redundant pathways for data without creating loops that would cause the network to fail. Perlman's elegant solution, which she developed in the 1980s, is still used in virtually every network today. She's been called the mother of the internet, though she herself finds the title amusing and somewhat embarrassing. But her contributions are undeniable. She's written textbooks on network design that are used in computer science programs worldwide. She holds over 100 patents. She continues to work on network security and protocol design. And yet, most people, even many people working in technology, have never heard of her. Frances Allen was the first woman to win the Turing Award, computer science's equivalent of the Nobel Prize, for her work on compiler optimization. A compiler is a program that translates code written in a high-level programming language into machine code that a computer can execute. Making compilers work efficiently is crucial for computer performance. Allen pioneered techniques for optimizing compilers, making programs run faster and use less memory. Her work on program optimization laid the groundwork for techniques that are used in every modern compiler. She worked at IBM for over 4 decades, mentoring generations of computer scientists. When she won the Turing Award in 2006, she was 74 years old. The recognition came late, but it acknowledged the fundamental importance of her contributions to computer science. Barbara Liskov won the Turing Award for her contributions to programming languages and distributed computing. She developed the concept of abstract data types, which fundamentally changed how programmers think about organizing code. She created the Liskov substitution principle, one of the fundamental principles of object-oriented programming that is taught in every serious computer science program. Her work on distributed computing, systems where multiple computers work together to solve problems, laid the foundation for cloud computing and many of the large-scale systems we rely on today. She's been a professor at MIT for decades, where she's trained hundreds of graduate students who have gone on to influential careers in computer science. Her work demonstrates that the highest levels of theoretical computer science are not the domain of one gender. Excellence is gender neutral. Shafi Goldwasser won the Turing Award for her work on cryptography and complexity theory. Cryptography is the science of secure communication, and it's absolutely crucial for modern digital life. Every time you make a purchase online, every time you send an encrypted message, every time you log into a secure website, you're relying on cryptographic techniques. Goldwasser's work on probabilistic encryption and zero-knowledge proofs revolutionized the field. A zero-knowledge proof is a way to prove that you know something without revealing what that something is. This might sound paradoxical, but it's mathematically possible, and Goldwasser was one of the pioneers in developing these techniques. Her work is deeply theoretical, involving complex mathematics, yet it has profound practical applications in computer security. She's a professor at MIT and the Weizmann Institute of Science, and she continues to push the boundaries of what's possible in cryptography and computational complexity. In artificial intelligence, Fei-Fei Li transformed computer vision and led the creation of ImageNet, the dataset that enabled the deep learning revolution we're experiencing today. Before ImageNet, computer vision systems struggled to recognize objects in images. Li realized that what was needed was a much larger and more diverse training dataset. She led a massive effort to create ImageNet, a database of millions of images labeled with what objects they contained. When ImageNet was released and used in computer vision competitions, it sparked rapid progress in the field. Deep learning systems trained on ImageNet began to achieve human-level performance on object recognition tasks. This breakthrough enabled countless applications, from facial recognition to autonomous vehicles to medical image analysis. Li didn't just contribute to artificial intelligence, she enabled a revolution in the field. She's now co-director of Stanford's Human-Centered AI Institute, where she's working to ensure that artificial intelligence is developed in ways that benefit humanity. Daphne Koller pioneered probabilistic graphical models, a mathematical framework for reasoning under uncertainty. Many real-world problems involve making decisions when you don't have complete information. How do you diagnose a disease when symptoms could have multiple causes? How do you recommend products when you don't know exactly what a user wants? Probabilistic graphical models provide a principled way to handle these uncertain situations. Koller's work made these techniques practical and applicable to real-world problems. She's also co-founded Coursera, the online learning platform that has brought education to millions of people worldwide. Through Coursera, she's helped democratize access to education, making it possible for people anywhere in the world to learn from the world's best universities. She later founded Incitro, a company using machine learning to accelerate drug discovery. Her career demonstrates the breadth of contributions that computer scientists can make, from theoretical foundations to practical applications to societal impact. Timnit Gebru's work on algorithmic bias and AI ethics is reshaping how we think about responsible AI development. As artificial intelligence systems become more powerful and more widely deployed, understanding their biases and limitations becomes crucial. Gebru's research has shown that facial recognition systems have much higher error rates for dark-skinned individuals and women. She's documented how AI systems can perpetuate and amplify societal biases. Her work has influenced how major tech companies think about AI ethics and fairness. She co-founded Black in AI, an organization supporting Black researchers in artificial intelligence. Her willingness to speak truth to power, even at personal cost, has made her a leader in the movement for more ethical and accountable artificial intelligence. The future of AI will be shaped not just by technical innovations, but by ethical frameworks, and Gebru is at the forefront of developing those frameworks. In cybersecurity, Katie Musuri developed the framework for vulnerability disclosure programs used by Microsoft, the Department of Defense, and companies worldwide. When security researchers discover vulnerabilities in software, there needs to be a responsible way to disclose those vulnerabilities so they can be fixed before malicious actors exploit them. Musuri created the policies and procedures that make this possible. Her work has made software more secure for billions of users. Parisa Tabriz, known as Google's security princess, leads Chrome security. The Chrome browser is used by billions of people, and keeping it secure is a monumental challenge. Tabriz and her team work to identify and fix security vulnerabilities, to design security features that protect users without making the browser harder to use, and to stay ahead of attackers who are constantly looking for new ways to compromise systems. Her work demonstrates that the highest levels of technical security expertise are not gendered. The ability to think like an attacker, to find vulnerabilities, to design secure systems, these skills don't depend on whether you're male or female. These women aren't just contributing to computer science, they're defining its future directions, they're solving the hardest problems, they're leading the most important research, they're training the next generation of computer scientists, they're starting companies, they're influencing policy, they're reshaping how we think about technology and its role in society. And they're not exceptions. For every woman I've named, there are dozens more making crucial contributions. The problem isn't that women can't do computer science at the highest levels. The problem is that many women who could make these contributions never get the opportunity, or they leave the field because the environment is hostile or unwelcoming. We're losing talent, and that loss affects everyone. But here's another twist in our story. While we celebrate individual exceptional women, we need to recognize that the question, are women better computer scientists than men, is fundamentally flawed. It assumes that gender is a meaningful predictor of ability in computer science. It's not. What matters is individual talent, interest, education, and opportunity. There are brilliant computer scientists of all genders. There are mediocre computer scientists of all genders. Gender doesn't determine your capacity for logical thinking or creative problem solving any more than it determines your capacity for kindness or courage. Asking whether women are better or worse at computer science is like asking whether people with brown eyes are better or worse at computer science. It's a category error. Gender is one aspect of someone's identity, but it doesn't predict their abilities in any meaningful way. The real question we should be asking isn't whether women are better or worse at computer science. It's why we've created a field where women's contributions are consistently undervalued and their participation is systematically discouraged. Let's examine the systemic barriers that keep women out of computer science. It starts early. By age 6, girls are less likely than boys to view their own gender as really, really smart, according to research on gender stereotypes. This isn't because girls are less smart. It's because they've already internalized messages from media, parents, and teachers about who is expected to excel in technical fields. Children at this age are forming their identity and their sense of what's possible for them. When they see that scientists and engineers in movies and TV shows are almost always men, when the books they read feature male inventors and male computer scientists, when the toys marketed to them reinforce gender stereotypes, they begin to internalize these messages. Girls start to think that science and technology are boy things. Boys start to think that only they can be engineers and programmers. These early stereotypes are remarkably persistent. They shape the choices children make throughout their education, often in ways that children themselves aren't consciously aware of. In elementary school, boys are more likely to be given computers and encouraged to explore them. Teachers, often unconsciously, call on boys more often in math and science classes. Boys are praised for their intelligence when they succeed. Girls are praised for working hard. This difference matters because it shapes how children interpret failure. When boys struggle, they think they just need to try harder. When girls struggle, they think they might not be smart enough. These patterns are not about individual malice. Most teachers genuinely want to support all their students. But unconscious biases influence behavior in subtle ways. Eye contact, tone of voice, who gets called on, who gets more detailed feedback. All of these tiny behaviors add up to send powerful messages about who belongs in which subjects. In middle school, girls report less confidence in their computer skills even when their actual skills are equal to boys. Confidence gaps emerge even when performance gaps don't exist. This confidence gap has real consequences. Students who lack confidence are less likely to take advanced courses, less likely to persist when material is challenging, less likely to seek help when they need it. In high school, girls are less likely to take advanced computer science courses, partly because they perceive the field as male-dominated and unwelcoming. In schools that offer advanced placement computer science, the classes are typically 70 to 80% male. The few girls in these classes often report feeling isolated, like they don't belong, like they have to work twice as hard to prove themselves. Some girls who might be interested in computer science never take the class because they don't want to be the only girl or one of very few. These social dynamics of the classroom matter. If a girl looks into a computer science class and sees all boys, she might assume that the class isn't for her, even if she's interested in the subject. Stereotype threat comes into play here too. Girls in predominantly male computer science classes experience performance anxiety that their male classmates don't, simply because they're constantly aware of being judged as representatives of their gender rather than as individuals. When women do enter computer science programs in college, they often find themselves in an unwelcoming environment. They may be the only woman in a class, or one of very few. They experience what's called imposter syndrome at higher rates than men, feeling like they don't belong, or that their success is due to luck rather than ability. They may have male classmates who assume they're less technical, or who talk over them in group projects. They may have professors who unconsciously call on male students more often, or who express surprise when women excel. One woman described her experience. "I felt like I had to prove myself constantly. My male classmates could make mistakes and it was fine, but if I made a mistake it felt like I was confirming everyone's suspicions that women couldn't code." These aren't always overt acts of discrimination. Often they're subtle, cumulative microaggressions that create a constant background stress that their male peers don't experience. A microaggression might be someone assuming a woman in a computer science class is studying education technology rather than core computer science. It might be a study group that forgets to invite the women in the class. It might be a comment about how someone doesn't look like a programmer. Each individual incident might seem trivial, but they accumulate. Research on workplace culture in tech companies reveals similar patterns. Women in tech companies report being interrupted more in meetings than their male colleagues. They report having their ideas attributed to male colleagues, a phenomenon so common that it has a name: heap-eating, when a man repeats a woman's idea and gets credit for it. They report being assigned less technically challenging work, being passed over for promotions in favor of less qualified men, being paid less than men with equivalent qualifications and experience. They face what researchers call the double bind. If they're warm and communal, they're seen as less technically competent. If they're assertive and direct, they're seen as abrasive or difficult. Men don't face this double bind. They can be assertive without being punished for it. A man who is direct and confident is seen as a leader. A woman who behaves identically is seen as pushy or aggressive. Women also face the prove it again problem. While men's competence is assumed until proven otherwise, Women must repeatedly prove their technical abilities. One mistake from a woman is seen as evidence that women can't code. Multiple mistakes from a man are seen as individual failures, not evidence about all men. A woman who succeeds might be told she was lucky or that the project was easy. A man who succeeds is seen as talented. These double standards are often unconscious. People don't deliberately set out to evaluate women more harshly, but research using identical resumes with male and female names has consistently shown that people rate the male resumes as more competent and recommend higher starting salaries, even when the resumes are identical in every other way. These biases affect hiring, promotion, salary decisions, and everyday interactions. They create an environment where women constantly have to work harder to achieve the same recognition. Sexual harassment remains a persistent problem in tech. High-profile cases at companies like Uber, Google, and others have revealed cultures where harassment was tolerated or covered up. Women who reported harassment faced retaliation, while perpetrators were protected because they were seen as valuable to the company. A survey by the Pew Research Center found that half of women in STEM jobs have experienced gender discrimination at work, and 3/4 of women in computer jobs have experienced such discrimination. These aren't isolated incidents, they're systemic problems. Even when harassment isn't present, women often find themselves excluded from informal networks where information sharing and mentorship happen. The after-work drinks, the weekend hackathons, the casual conversations where opportunities are discussed, these often happen in male-dominated spaces where women either aren't invited or don't feel comfortable. This exclusion has real career consequences. Advancement in tech often depends not just on your technical skills, but on who knows you, who advocates for you, and who includes you in opportunities. The venture capital world, which funds startups, is overwhelmingly male. Over 90% of venture capital decision-makers are men. Startups with all-male founding teams receive vastly more funding than those with women founders, even when the business plans are identical. Studies where investors evaluate identical pitches given by male and female entrepreneurs show that investors ask male entrepreneurs questions about potential for gains and ask female entrepreneurs questions about potential for losses. This difference in questioning leads to different funding outcomes. Investors are more likely to fund entrepreneurs they ask about potential gains. This means that women's ideas, innovations, and companies are systematically undervalued and underfunded. When venture capitalists look for the next Mark Zuckerberg or Elon Musk, they're looking for men who fit a particular profile. Women entrepreneurs, even equally qualified ones, don't fit that profile and struggle to get funded. The technologies that get built, the problems that get solved, and the products that reach market are disproportionately shaped by male perspectives. We're not getting the best technology, we're getting male-dominated technology, and we're all poorer for it. When women leave tech or never enter it, we lose not just their individual contributions but the diverse perspectives that lead to better products and more comprehensive solutions. Consider facial recognition technology. Early systems were trained primarily on images of white men. They performed poorly on women and people of color because the developers didn't adequately test on diverse populations. If the development teams had been more diverse, these problems would have been caught earlier. Or consider voice recognition systems that struggle to understand women's voices because they were trained primarily on male voices, or medical algorithms that underdiagnose conditions in women because the training data came primarily from male patients, or crash test dummies designed on male bodies that leave women more vulnerable to injury in car accidents, or office temperature settings optimized for male metabolism that leave women shivering. These aren't just technical problems. They're consequences of who gets to build technology and whose perspectives are centered in the development process. Diversity isn't just a nice to have, it's essential for building technology that works for everyone. Studies have consistently shown that diverse teams are more innovative, more creative, and better at problem solving. They make better products, they understand markets better, and they avoid costly mistakes. A study by Boston Consulting Group found that companies with diverse management teams have 19% higher revenues from innovation. A study by McKinsey found that companies in the top quartile for gender diversity are 25% more likely to have above-average profitability. These aren't small effects. They're large, consistent, and well-documented. Yet despite knowing this, despite decades of diversity initiatives, tech remains stubbornly male-dominated. Why? Partly because changing culture is hard, partly because people in power are often reluctant to share that power, partly because unconscious bias is difficult to overcome even with good intentions, and partly because the pipeline problem is real. When fewer girls study computer science in school, fewer women are available to hire in industry, which perpetuates the cycle. But there are success stories we can learn from. Some universities have dramatically increased the percentage of women in computer science by changing how they teach introductory courses. Instead of assuming students have prior programming experience, which boys are more likely to have, they offer multiple entry points for students with different backgrounds. Instead of emphasizing competition and individual achievement, they emphasize collaboration and real-world applications. Instead of teaching programming in isolation, they connect it to other fields like biology, art, or social science. These changes don't lower standards. They just remove arbitrary barriers that were excluding talented students, and the results are dramatic. Carnegie Mellon University, for example, went from having about 7% women in computer science in the mid-1990s to nearly 50% by implementing these kinds of changes. Harvey Mudd College achieved similar results. These examples prove that when institutions make genuine, sustained efforts to be more inclusive, they can succeed. In industry, some companies have made real progress on inclusion by implementing structured interviews that reduce bias, by setting diversity goals and holding leaders accountable for meeting them, by creating mentorship and sponsorship programs for women, and by having zero tolerance for harassment. These efforts work when they're genuine, sustained, and supported from the top. They fail when they're superficial, when they're just about optics, or when they're undermined by a culture that doesn't actually value diversity. The key insight is that talent is equally distributed, but opportunity is not. There are just as many girls with the potential to be brilliant computer scientists as there are boys. The difference is in who gets encouraged, who gets access, who gets support, and who gets welcomed into the field. When we create environments that welcome everyone, when we remove barriers and address bias, we see that women can excel in computer science at the same rates as men. So we arrive at our climax, the heart of the matter. The question, are women better computer scientists than men, is the wrong question. The right question is, how can we create a field that welcomes and supports talented people regardless of gender? How can we build systems that recognize and reward ability without bias? How can we ensure that technology serves all of humanity, not just the demographic that currently dominates its creation? The evidence is overwhelming. Women have been essential to computer science from its very beginning. They've invented fundamental concepts, led breakthrough research, and built world-changing technologies. When given equal opportunity, they perform at levels equal to or exceeding their male peers. The disparities we observe aren't due to differences in ability. They're due to differences in opportunity, encouragement, and environment, and those are things we can change. Imagine a world where girls grew up seeing as many women computer scientists as men in their textbooks and media, where parents encourage their daughters to code with the same enthusiasm they show their sons, where computer science classrooms were designed to be welcoming to all learning styles, not just the competitive, individualistic style that appeals to many young men, where tech companies actively work to create inclusive cultures, to eliminate bias from hiring and promotion, and to address harassment swiftly and seriously, where venture capitalists funded ideas based on merit, not on whether the founder reminds them of a young version of themselves. What would that world look like? We don't know for certain, but we can make some educated guesses. We'd have more computer scientists overall, accessing a larger talent pool. We'd have better technology, designed with more diverse perspectives and needs in mind. We'd have different problems getting prioritized and solved. Maybe we'd have better educational software because women make up the majority of teachers and would bring that perspective. Maybe we'd have better healthcare technology because women are the primary healthcare decision makers in most families. Maybe we'd have better tools for collaboration and communication because women tend to value those skills highly. These aren't stereotypes about what women naturally care about. They're observations about the perspectives and experiences that are currently underrepresented in tech. We'd also likely see innovation in areas we haven't even thought of yet. That's what diversity does. It doesn't just add perspectives we already value. It introduces entirely new ways of thinking about problems. Some of the most significant breakthroughs in science and technology have come from outsiders who approach problems differently because of their different backgrounds and experiences. The business case for diversity in tech is compelling. Companies with more diverse teams are more innovative, more profitable, and better at problem solving. They make better products, understand markets better, and avoid costly mistakes. This isn't speculation. It's been demonstrated in study after study across industries. Yet despite knowing this, despite decades of diversity initiatives, tech remains stubbornly male-dominated. Why? Partly because changing culture is hard. Partly because people in power are often reluctant to share that power. Partly because unconscious bias is difficult to overcome even with good intentions. And partly because the pipeline problem is real. When fewer girls study computer science in school, fewer women are available to hire in industry, which perpetuates the cycle. But examples like Carnegie Mellon and Harvey Mudd show that change is possible when institutions commit to it. Now we reach our resolution. So are women better computer scientists than men? No, and men aren't better than women. Computer science ability isn't determined by gender. It's determined by individual aptitude, interest, education, and opportunity. The variations within each gender are far greater than any average differences between genders. You can't predict someone's programming ability from their gender any more than you can predict their favorite food or their musical talent. What we can say is this: women have been essential to computer science from its very beginning. They've made foundational contributions that shape everything we do with computers today. They continue to be leaders in research and industry, pushing the field forward. When women are underrepresented in computer science, we all lose. We lose their perspectives, their innovations, and their solutions to problems we didn't even know we had. The goal shouldn't be to prove that women are better or that men are better. The goal should be to create a field where anyone with talent and interest can contribute, regardless of their gender. Where decisions about hiring, promotion, and funding are based on merit, not on bias or stereotypes. Where the culture is welcoming and inclusive, where harassment is not tolerated, and where everyone has equal opportunity to succeed. This isn't just about fairness, though fairness matters. It's about building the best possible technology with the most talented people we can find. It's about solving the hardest problems humanity faces with the full range of human creativity and intelligence. It's about creating a future where technology serves everyone because everyone had a hand in creating it. What can you do? If you're a student considering computer science, don't let stereotypes discourage you. If you're interested in solving problems, in building things, in understanding how technology works, then computer science might be for you, regardless of your gender. Seek out welcoming communities and programs. Find mentors who support you. Remember that struggling with difficult concepts doesn't mean you don't belong. It means you're learning. Everyone struggles with difficult concepts. The difference is that some people are given more encouragement to persist through the struggle. If you're feeling like an imposter, remember that many of the most successful people in any field have felt that way at times. Imposter syndrome is a sign that you're challenging yourself, not a sign that you don't belong. If you're a teacher or professor, examine your own biases. Are you calling on male students more often? Are you assuming male students are more technical? Are you presenting computer science in ways that appeal to diverse interests? Small changes in how you teach can have significant impacts on who feels welcome in the field. Use examples and applications that connect to diverse interests. Emphasize collaboration and real-world impact, not just abstract theory. Provide multiple entry points for students with different backgrounds. Give equal encouragement and attention to all students. Challenge stereotypes when you hear them. Create a classroom culture where everyone feels they belong. If you're working in tech, be an active ally. Call out bias when you see it. Support and mentor women colleagues. Advocate for inclusive hiring and promotion practices. Listen to women's experiences even when they're different from yours. Amplify women's voices in meetings. Give credit where credit is due. Create opportunities for women to lead high-profile projects. Mentor junior women colleagues. Sponsor women for promotions. If you're in a position of leadership, make diversity and inclusion a genuine priority, not just a checkbox exercise. Set goals, measure progress, and hold people accountable. Create pathways for underrepresented groups to enter and advance in your organization. Address harassment and discrimination swiftly and seriously. Foster a culture where diverse perspectives are valued, not just tolerated. If you're a parent, encourage all your children to explore technology, not just your sons. Buy computers and coding toys for your daughters. Show them examples of successful women in tech. Challenge media that presents technology as only for boys. Talk to your daughters about careers in technology. Support their interests in science and math. Don't accept statements like, girls aren't good at math, or coding is for boys. These statements aren't facts. They're stereotypes that limit children's potential. The future of technology should be built by everyone, for everyone. To get there, we need to recognize that the barriers women face in computer science aren't about ability. They're about culture, opportunity, and bias, and those things can change. As you drift off to sleep tonight, think about the untold stories of women in computing. Think about the ENIAC programmers rewiring a room-sized computer by hand, inventing the foundations of software engineering without any of the tools we take for granted. Think about Ada Lovelace, envisioning the potential of computers a century before they existed. Think about Grace Hopper, creating the first compiler and fighting against, "We've always done it this way." Think about Radia Perlman, making the internet possible. Think about the countless women working in tech today, building the future despite the obstacles they face. And think about the potential that's being lost every day because talented girls are discouraged from pursuing computer science, because women leave the field due to hostile cultures, because innovation is limited to a narrow demographic. The question isn't whether women are better computer scientists than men. The question is how much further we could go, how much more we could achieve if we truly welcomed and supported everyone with the talent and passion to contribute. The answer is transformative. The technology we have today is impressive, but it's only a fraction of what's possible if we tap into the full range of human potential. Every girl who's discouraged from studying computer science, every woman who leaves tech due to a hostile environment, every brilliant idea that never gets funded because of bias represents a loss not just for that individual, but for all of us. We can do better. We must do better. The future is too important to build with only half of humanity's talent. So let's reframe our original question one last time. Instead of asking whether women are better computer scientists than men, let's ask, how can we build a future where everyone with the ability and interest can contribute to shaping technology? How can we ensure that the next generation of groundbreaking computer scientists includes people of all genders, all backgrounds, all perspectives? How can we create systems that recognize and reward talent wherever it's found, without bias or stereotype? These are the questions that matter. These are the questions that will determine whether we get the technology we need to solve the challenges we face. And the answers start with recognizing a simple truth. Talent knows no gender. Excellence in computer science isn't about being male or female. It's about curiosity, persistence, creativity, logical thinking, and the drive to solve problems. Throughout history, women have possessed these qualities in equal measure to men. They've invented, innovated, and transformed computing at every stage of its development. The fact that their contributions have often been overlooked or minimized doesn't diminish them. It only highlights how much work we still have to do in recognizing and supporting talent regardless of who possesses it. As computer science becomes ever more central to every aspect of our lives, from healthcare to education, from communication to transportation, from entertainment to governance, we need the best minds working on it. We can't afford to exclude half the population. We can't afford to let bias and stereotype limit who gets to shape our technological future. The stakes are too high. The challenges are too great. The opportunities are too vast. Imagine waking up in a world where computer science classrooms are equally filled with students of all genders, where tech companies have diverse teams at every level, where the AI systems that increasingly shape our lives are built by people who represent the full diversity of humanity, where the next breakthrough in computing might come from anyone because everyone has equal opportunity to contribute. That world is possible. It's not inevitable, but it's possible. It requires intentional effort, systemic change, and a commitment to recognizing and eliminating bias. It requires valuing diversity not as a box to check, but as essential to excellence. It requires building cultures that welcome and support everyone, not just those who fit traditional stereotypes. The history of women in computing teaches us several lessons. First, contributions can be invisible even when they're foundational. Recognition matters. The ENIAC programmers did groundbreaking work, but because it wasn't recognized at the time, their contributions were nearly lost to history. Second, who is encouraged to pursue a field shapes who enters it far more than any innate differences in ability. When programming was seen as clerical work for women, women did it. When it became prestigious work for men, men dominated it. The work didn't change, the perception did. Third, culture and perception can shift dramatically over time. What's considered men's work or women's work is culturally constructed, not biologically determined. Fourth, when we exclude groups from fields, we lose not just their individual contributions but the perspectives and approaches that could lead to entirely new directions. And fifth, change is possible. Fields can become more inclusive, barriers can be dismantled, cultures can shift, but only with sustained intentional effort. As you close your eyes and prepare for sleep, let these thoughts settle into your consciousness. Computer science isn't a male domain or a female domain, it's a human domain. The code that runs our world doesn't care about the gender of the person who wrote it. It only cares whether it works, whether it's elegant, whether it solves the problem it's meant to solve. The algorithms that power our technology don't have gender. Neither should the expectations about who can create them. The next time you use technology, think about who built it. Think about whose perspectives shaped it. Think about whose needs it serves best. And think about what might be different if the people building our technological future represented the full diversity of the people using it. Think about the smartphone in your pocket. Think about the social media platforms you use. Think about the search engines that answer your questions. Think about the streaming services that entertain you. Think about the GPS that guides you. All of these technologies were built by teams of people making countless decisions about how things should work, what features to include, what problems to solve, what use cases to optimize for. Every one of those decisions reflects the perspectives, experiences, and biases of the people who made them. When those teams are not diverse, when they don't represent the full range of humanity, their products reflect that limitation. We get technology that works great for some people and poorly for others. We get products that solve some problems while ignoring others. We get innovation in some areas while other areas remain neglected. Sleep now, knowing that excellence in computer science, like excellence in any field, is about individual talent, hard work, and opportunity, not about gender. Rest easy knowing that the future of technology doesn't have to replicate the biases of the past. Dream of a world where the question, "Are women better computer scientists than men?" sounds as absurd as it should, where we judge people on their abilities and contributions, not on stereotypes and assumptions. And when you wake, perhaps you'll see the world of technology a little differently. Perhaps you'll notice the hidden contributions, the excluded voices, the untapped potential. Perhaps you'll be part of the solution, part of building a more inclusive, innovative, and excellent field. The future of computer science isn't male or female, it's human, and it's waiting to be built by anyone with the vision and the skill to shape it. As you drift deeper into sleep, consider the progress we've already made and the work that still lies ahead. We've come a long way from the days when women were explicitly barred from universities, from professional societies, from careers in science and technology. We've made progress in recognizing contributions that were previously invisible. The ENIAC programmers have finally received recognition. Ada Lovelace is celebrated. Grace Hopper has a Navy ship named after her and a prestigious award in her honor. We have more women in computer science today than we did 50 years ago, even if we have fewer than we did 40 years ago. But recognition isn't enough. Awards aren't enough. We need systemic change. We need to address the barriers that keep women out of computer science and push women out of tech careers. We need to create environments where everyone can thrive. Think about what that means in practice. It means examining hiring practices for bias. Are job descriptions using language that unnecessarily signals gender? Are interview panels diverse? Are candidates evaluated on their potential or on narrow criteria that favor certain backgrounds? It means looking at promotion practices. Are women being passed over for promotions? Are their contributions being valued equally? Are they being given the same opportunities to lead high-profile projects? It means examining compensation. Are women being paid equally for equal work? Are salary negotiations being handled fairly? Is the motherhood penalty being addressed? It means creating inclusive cultures. Are meetings being run in ways that allow everyone to contribute? Are women's voices being heard and valued? Is harassment being taken seriously and addressed swiftly? Are there mentorship and sponsorship opportunities? These aren't abstract questions. They're practical issues that affect real people's careers and lives every day. As your consciousness drifts towards sleep, imagine the innovations we're missing because of the talent we're excluding. Imagine the medical breakthroughs that might come from women who bring perspectives on healthcare that men might miss. Imagine the educational technologies that might be developed by women who understand the needs of students and teachers because they've experienced those roles. Imagine the accessibility features that might be built by people who have different physical abilities or needs. Imagine the security protocols that might be designed by people who face different threats. Imagine the social platforms that might be created by people who prioritize different values. We don't know what we're missing because we don't know what isn't being built. But we know that diversity leads to innovation, that different perspectives lead to better solutions, that inclusion makes us all better off. Let your mind wander to the future we could build together. A future where a young girl interested in computers doesn't have to wonder whether she belongs. Where she sees herself reflected in her teachers, her textbooks, her media. Where she has role models who look like her and have succeeded in the field. Where she's encouraged and supported, not discouraged or overlooked. Where she can pursue her passion without constantly fighting against stereotypes and biases. A future where that girl grows up to be a computer scientist who makes contributions that change the world, and her contributions are recognized and valued, not minimized or attributed to someone else. A future where she mentors the next generation, creating a positive cycle instead of the negative cycle we have now. That future is possible. It requires all of us to do our part. It requires commitment, effort, and persistence. But it's achievable. As sleep overtakes you, remember that change happens through individual actions as much as through systemic reforms. Every person who challenges a stereotype, who mentors someone different from themselves, who speaks up against bias, who creates an inclusive environment, contributes to change. Every girl who pursues computer science despite the obstacles, every woman who persists in a tech career despite the challenges, every person who advocates for diversity and inclusion moves us closer to the future we want to build. You can be part of that change. You can be part of building a better future. The choices you make, the actions you take, the values you uphold, they all matter. They all contribute to the culture we create together. Good night, and dream of a world where talent is recognized and nurtured regardless of gender, where technology serves all of humanity because all of humanity helped create it, where the question we started with seems as absurd as it should. Dream of a future where computer science is truly inclusive, truly excellent, truly human. That future starts with understanding the past, recognizing the present, and committing to change. It starts with acknowledging that women have always been part of computing, that they've made essential contributions, and that we need their participation now more than ever. It starts with recognizing that the barriers they face are not natural or inevitable, but are human creations that can be dismantled. It starts with commitment to building something better. Sleep well, knowing that the future is not yet written. We write it together, every day, through our choices and our actions. The story of women in computer science is not over. It's still being written, and you can help write the next chapter.